Today we built the ingestion pipeline, which is the first real piece of product logic in our REG system. Ingestion is the entire point for all knowledge in REG system. We take a support document, the frequently asked question or a policy guide, anything in Markdown or plain text, and transform it into searchable vectors stored to Postgres. The pipeline has three stages. The first one is the chunker splits the documents into the overlapping segments because embedding models and LLMs have token limits, and because retrieval works better when each chunk is focused on one idea. Second is the embedder calls the OpenAI to convert each chunk into 1536-dimensional vector, which is a numerical representation of meaning. And at third, the store writes those chunks and their vectors to Postgres using PG vectors, so we can search them later by semantic similarity. When this episode is done, you will have two ways to index documents. The CLI path runs on your host machine, useful for local development and batch scripts. The HTTP path accepts file uploads through the API container, the production integration point. Success for us means you can ingest the frequently asked question from the terminal, open Postgres, and see rows with chunk text and embeddings. Then you can upload the same file via HTTP and get back JSON response with the document ID and chunk count. If you open the db migration 001 chunks.sql, this is the plain SQL executed by migration runner. The columns are the ID, which is UUID primary key, the doc ID, which groups all chunks from a single ingest run. When you index a frequently asked question, every chunk from that file gets the same doc ID. Source is the file name. Chunk index is the order with the document, 0 for the first chunk, 1 for the second, and so on. Text is the actual chunk content. Metadata is a JSON-B column where we store allowed roles for future access control, responsible for which user roles can see this chunk. Embeddings is a vector with 1536 dimension, I have already mentioned that above, and content TSV is an auto-generated TSV vector, which is the Postgres data type for full text keyword search, which we will use in a hybrid retrieval a bit later, created at just a timestamp. We create two indexes. The first is the B tree on the doc ID because the pipeline deletes old chunks by doc ID before inserting new ones. The second is a generalized inverted index, the GIN one, on the content TSV for the fast keyword search. Before we write the chunker, let me show you the configuration that controls chunk size and overlap. Open the API config py. This is the pydantic settings class that loads environment variables from the .env file. The fields are the OpenAPI key for the embedding API, database URL for the Postgres, Redis URL for caching later, and embedding model defaults to text embedding free small we are using. LLM model for generation, chunk size is the 512 and chunk overlap is the 64, and a few retrieval parameters we will use in upcoming videos. So we use this settings object as a model level singleton. Every part of the application imports this one instance, so changing chunk size or embedding model is one line edit in .env file, but not the entire code change. In the last episode, we covered why REG systems chunk documents and embed them as vectors. Today, we implement that pipeline, so let's make a quick theory refresh on that mechanics. Chunking is necessary because models have limits. OpenAI text embedding free small accepts up to 8,191 tokens per one call, roughly 6,000 words. But retrieval works better with focused chunks. If you embed an entire 20-page manual as one vector, a query about password resets will match weakly because most of the document is about other topics. If you split that menu into 500 character chunks, the password reset sections becomes its own vector. The semantic search can rank it highly, and we use 512 characters as a default. Usually 3 or 5 sentences, enough for a complete meaning without too much drift. Overlap is the second piece. Our chunker uses a sliding window. It advances by chunk size minus overlap, so consecutive chunks share a tail. If chunk 0 ends mid-sentence and chunk 1 starts 64 character earlier, the boundary sentence appears in both chunks. This prevents facts from being split across a cut. Overlapping chunks increase storage and API calls by about 15 to 20% because you are embedding some text twice. The benefit is that retrieval does not miss information that happens to land on a boundary, a worthwhile trait for the most RG system. If you open Ingestion chunk in Py, you will see that the text chunk data class is a lightweight container for one chunk. It holds the text, chunk index, source file name, doc ID, metadata dictionary, and optional embedding and ID fields that get filled later in this pipeline. The chunk test function does the sliding window split. It validates the chunk size is positive and overlap is smaller than chunk size. Then it normalizes line endings and strips white spaces. The main loop starts at position 0 and advances by step, which is chunk size minus overlap. For our defaults, that is 512 minus 64, so 448 characters per step. Each iteration extracts a substring from start to start plus chunk size, strips it, and wraps it in a text chunk. The chunk index increments with each piece. The metadata includes source, doc ID, chunk index, and allowed rows, which defaults to support and admin. Because the step is smaller than chunk size, consecutive chunks share a tail. That overlap, 64 characters shared between consecutive chunks, is what prevents boundary effects from being lost. Once we have chunks, we need to embed them. Open the Ingestion embedded Py. By embedded text function takes a list of strings and returns a list of float arrays, one vector per input. If the input is empty, it returns an empty list immediately without calling the API. If the OpenAPI key is missing, it raises a clear error. The function uses the official OpenAI SDK. It calls embeddings create with the model from setting, the text embedding free small by default, and passes all text in one request. The API accepts up to 2048 text per call, so for most documents this is a single batch. The response is a list of embedding objects. We extract the embedding field from each one and return the list of factors. Batching is important for latency. If you call the API once per chunk, a 50 chunk document takes 50 round trips. Batching all 50 chunks into one call reduces that to one round trip. Now when we have chunks and vectors, the store should write them to Postgres. Open Ingestion store. The save chunk function persists chunks to the database. It opens the PsychoPG connection and registers the PG vector adapter. That adapter tells how to serialize Python float lists to Postgres vector types. Without it, the insert would fail. The function starts by deleting all rows with the same doc ID. The delete then insert button handles updates. If you indexed a frequently asked question, then edit it and index it again, the old chunks are removed before the new ones are inserted. This avoids orphaned rows and duplicate detection logic. Then it loops over the chunks and inserts each one. The insert statement includes ID, doc ID, source, chunk index, text, metadata as a JSON, and embedding as a vector. The function requires that chunk embedding is not none before saving. If you forget to call the embedder, you get a clear error here. After all inserts, it commits the transaction and returns the count of the row saved. Now, if we will have a look at Ingestion pipeline Py, we will see that this is the single entry point for ingestion. The pipeline orchestrator ties these pieces together. Without it, the CLI and HTTP route would duplicate the migrate chunk embedded save sequence, and with it, both paths call the same function. The ingest text function runs 5 steps. The first step, it calls run migrations to ensure the schema is current. Second is generates the fresh UUID for the doc ID. Third, it calls chunk text with the setting for chunk size and overlap. Fourth, if there are no chunks, it returns early with the 0 count. Fifth, it calls the embed function, which defaults the embed text but can be mocked for tests and zips the resulting vectors onto the chunks. Sixth, it calls the same chunks to persist everything. And seventh, it calls invalidate cache, which is hook for the caching layer we built in upcoming videos. Now let's wire up the CLI and HTTP path. If we open Ingestion CLI Py, this is a command line interface for ingestion. It uses argparse to define the subcommand called ingest. The subcommand takes a path argument and an optional roles flag. The main function parses the arguments, calls ingests file from the pipeline, and prints the result. Now let's open API routes ingest.py. This defines a post endpoint at /ingest. It accepts a multi-part file upload. The function reads the file with await file read, decodes it at UTF-8, and calls ingest text from the pipeline. The result is mapped to an ingest response pydantic model, which defines the JSON shape, doc ID, source, and chunk count. The root uses fast API dependency injection. The settings parameter is injected via depends get settings, which is defined in API deps.py. That model also prepares the SQL Alchemy session factory for future ORM-based routes, so we do not use it in ingestion. So I am in a terminal. First I run the CLI ingest command with the frequently asked question file. The command is uv run python -m ingestion CLI ingest data sample frequently asked question.md. It prints ingest 5 chunks from the file. That means the pipeline ran successfully. The file was chunked, embedded, and saved to Postgres. Now I ingest a second file, policies.md. Same command, different path. It prints ingested 7 chunks from policies.md. So we have 12 chunks total across 2 documents. Let me verify that the roles are actually in the database. I run the doc and compose execute with those 12 commands, and the output is 12 chunks are persisted. Now let me show you the chunking split in detail. This is the key insight of the episode. Here is the frequently asked question as one file. After ingest 5 chunks, I will query Postgres to show the full text of each chunk in order. Watch the lockout sentence. In the original file, it reads, after 5 failed attempts in 50 minutes, the account is locked for 30 minutes. Contact support if you need an immediate unlock. Chunk 0 starts with the top of the frequently asked question and stops after 512 characters. It cuts mid-sentence at contact that is normal for fixed-size chunking. Chunk 1 does not start as chunk 0 ended. It starts earlier with the shared tail, which is PTS in 15 minutes. The account is locked for 30 minutes. Contact support if you need an immediate unlock. That phrase appears in both chunk 0 and chunk 1. That repeat is the overlap. That is how chunking works in the application. The overlap window is 64 characters, as you remember from the previous section. So if the fact sits on the boundary, like locked for 30 minutes, it still appears in both chunks. Retrieval can find them from either side. Chunk 4 is shorter, 185 characters, because it is the last window of the file. No padding. 1 file, 5 chunks, visible overlap at every boundary. That is the ingestion pipeline in action. Now let us quickly take a look on HTTP path. We just need to run this curl with the file, and we see that API returns JSON with doc ID, source, and chunk count. Same pipeline, different entry point. The ingestion pipeline is complete. Documents are chunked, embedded, and stored in Postgres with pgvector. The knowledge base is ready. Next video we search these chunks. If you found this video helpful, learned something new, or discovered ways to simplify your workflow, boost your productivity, or even save money, please subscribe my channel and hit the like, because it really helps me to grow and keep digging to discover new things and continue creating more content like this. Also, leave a comment below with your thoughts, questions and experiences. My goal is for us to learn, grow and build real AI expertise together, and your feedback is an important part of that. Thanks for watching and see you in the next videos.